Good afternoon, everyone. Now we will see one more important integrated rate equation, that is the first order rate kinetics. This is very important. First order reaction or first order rate kinetics. What is the first order reactions? Whose concentration power or order should be equal to 1, means it depends only on one reactant concentration. A reaction that depends on the concentration of only one reactant. Means here whose power is 1 and order of the reaction is 1. Again, let us take here one reaction. A is giving product. Then for this reaction we can write rate is equals to K into A power 1. Right, because anyhow we are saying that it is a first order reaction. For first order reaction we can write rate is equals to K into A power 1. Again we will derive the integrated rate equation for first order reaction. Let us assume at t equal to 0, at initial time the concentration of A equal to A0, and after some time t the concentration, some x amount is consumed, then it can form some x amount. Sometimes we can represent this A0 as A0, and at a time t we can represent this as AT. We can take anything, either small a0 minus x, and this one. Both are correct only. But amount of product formed, that is the x. We can write rate equation again. Rate is equals to minus decreasing in concentration of A by dt. Nothing but what I can write d change in concentration A0 minus x and minus A0 by dt. That nothing but A0 cancel, minus plus dx by dt. Again here dx by dt or minus dA by dt, nothing but it is rate. That is equals to what? Concentration of there is a rate constant into concentration of A power 1. To derive the integrated equation, let me write this equation like this. Let me take with the dA by dt. Is equals to K into concentration of E. Now we will separate the terms. dA by all concentration terms one side and K into dt. You bring the minus this side. dA by A is equal to minus K into dt. Now you apply integration. So in the limits, initial concentration A0 to final concentration AT, d of A by A is equals to minus of K will come out, integration time. So at A0 initial time is 0, at t AT the time is t and dt. So integration of dA by A means what? It is ln of A. The mathematical formulas, ln of A. So within the limits of A0 to AT, so we can write this ln of A t minus ln of A0, ln of AT minus ln of A0, that is equals to minus K, again 0 to t, integration of dt means t, so 0 to t means you will get directly kt. This we can write, if you bring the minus this side, you will get ln of A0 minus ln of AT is equals to kt. Finally we can write this ln of A0 by AT is equals to KT. This is one equation in terms of logarithms. And if you remove this ln into the log 10, ln means here log base e, and that you convert into log base 10, we will get 2.303 log A0 by AT is equals to KT. From this we can write the rate constant K is equals to 2.303 by T log of A0 by AT, and this is the formula to calculate the rate constant for first order reaction. This we can write in another form where K equal to 2.303 by T log A naught means you can write in terms of small a, A0, AT means the concentration A0 minus X. And this is also important form. So both are important. We can represent here A0 minus X, but here we are representing with AT. Now further we can derive some more formulas here. We have ln AT minus ln A0 equal to KT. So we got this one, this minus KT. From this you can write ln AT by A0 equal to minus KT. Your formula ln A minus ln B, you can write ln A by B, and if you remove this ln, natural logarithm, what you will get AT by A0 is equals to e power minus KT. So from this AT, concentration of reactant A at a time t is equals to A naught into e power minus KT. Is the amount of reactant left after time t, A0 into e power minus KT. This is exponential form. These formulas are exponential formulas. Now amount of product formed, that is X value. What is X? X equal to A naught minus AT. This is the amount of A consumed, or you can say the amount of A reacted, and this is the amount of A left. You can write this A naught minus AT means again you can write A naught into e power minus KT. That nothing but you can take A naught comma 1 minus e power minus KT. So amount of reactant reacted at a time t is equals to, this is the one. So you can write X is equals to A naught into 1 minus e power KT. So we can write one more formula. This is very rarely they will ask you, degree of dissociation. In case of first order reaction, degree of dissociation. What is the formula? Alpha is equals to degree of dissociation, number of moles after dissociation or association. What are the number of moles after association, dissociation? Form X. And initial number of moles means here concentration, the concentration after some time by initial concentration, that is the degree of dissociation. That is equals to, you can write the formula X means A0 into 1 minus e power minus KT, and this is A0. A0 they will anyhow get cancelled out. What left? 1 minus e power minus KT, and this is a degree of dissociation for first order reaction. Now next we will see half-life. Half-life for first order reaction, and this is half-life for first order reaction also very important. T of, or we can use your T 50%. Again, what is half-life? It is the time required to consume half of the initial reactant. So we have the formula, rate constant K is equals to 2.303 by T log A0 by AT or A0 by A0 minus X. You can take any one. Let us assume if time T is equals to T off, then in that case the concentration of AT is A0 by 2. At half of the time, the amount of reactant left is half of its initial concentration, A0 by 2. And these two values if you substitute in that rate constant equation, then you will get K equal to 2.303 by T in place of T, you can write to T off and log of A0 by A0 by 2. And from this, T off is equals to 2.303 by K, and this is log A0 cancel log 2. Log 2 means what? 0.3. So that can give overall 0.693 by K. So half life of first order reaction is 0.693 by K. And this is very important formula for first order reaction. And from this we can understand that T off, here there is no concentration, there is no initial concentration terms. So T off is directly proportional to concentration power 0 or simply A power 0. Means what? Here half life of first order reaction is independent on initial concentration. But whereas a zero order reaction case, half life is directly proportional to initial concentration, but half life of first order reaction is independent. This statement is very important on initial concentration of reactant. So very important statement. So if the half life of first order reaction is independent on initial concentration, then we can derive the various formulas here. Let us assume initially we have 100% of the reactant, and after half of the time and 50% left. This is the T 50%. The time required to complete 100 to 50. Again to convert 50 to 25, how much time it will take? We know that T off is independent on the initial concentration, whether it is 100 or 50 or 20 doesn't matter, always half life is constant. So 50 to 25, again one more half life. So again here the time required is T 50%, same. But whereas in case of the zero order reaction, that is half of the initial half life, but here all half lives are same. Again if you convert 25 to further 12.5, so here the same half life, again T 50%, again you convert 12.5 to next 6.25, again T 50%, and so on. It will go like this, so on. Now one more, 100 to, if you come directly to 25, how much time it will take? 100 to 25 means how much consumed? 75% is consumed. That is nothing but year 1 half life, year 1 half life. So that is equals to 2 times of half lives. So in case of first order reaction, T 75% is equals to twice the T 50%. Similarly, T 100 to this one, 12.5. So how much consumed? 87.5. So you can write T 87.5% is equals to 3 half lives in case of this first order. Again here to here, how much this one? T 93.75, so 75, and that is equals to 4 times of T offs, and so on. And in between we have T 87.5 and T 93.75. We'll get T 90%. That we can write here another formula. T 90 percentage, I will write it directly here, that is equals to almost 3.33 times. It is more than 87 and less than 93 percentage. So you can take 3.3 in between 3 and 4. 10 by 3 times of T 50 percentage. Next, T 99 percentage is equals to 20 by 3 times of T 50 percentages, and T 99.9 percentage is equals to 10 times of T 50 percentage. Again, this is very important. T 99.9 is equals to 10 times of T 50 percentage, and so on again. We can write other relations here, that is T 99 percentage is equals to 2 times of T 90 percentage, and T 99.9 percentage is equals to 3 times of T 90 percentage, and T 99.99 percentage is equals to 4 times of T 90 percentage, again so on. And if you come to the T 100 percentage, here T 99.9 percentage, if you go for T 100 percentage, that is the completion of the reaction. So it will take infinity times of half-lives. Means first order reactions never undergo completion. So every time half of the reaction will consume, half of the reaction will take half-life. There is no completion of the reaction, and this is also very important. In case of zero order reaction, for the completion we require 2 half-lives, but whereas in case of the first order reaction, there is no completion of the reaction, it will take infinity times of half-lives. And this one and this one, and they are important. These relations we can derive in another form also. We can use these relations because we have the formulas. The time required to complete some x percentage of the reaction, let us assume. We have reactant and some x percentage of the reactant consumed, then T x percentage we can write according to first order 2.303 by K, and log, let us assume initially we have 100 percentage of the reactant, then if x percentage is consumed, then we can write 100 minus x. Similarly, so y percentage of reactant is consumed, then the formula 2.303 by K log 100 by 100 minus y. Now you take equation, let us assume both the equation T x percentage by T y percentage will be equal to log of 100 by 100 minus x. Anyhow, these two will get cancelled out, 2.303 by K and 2.303 by both the K is the same, that will be cancelled out, and log of 100 by 100 minus 1. And by using this relation also we can identify, we can find out those relations, that is the T 75 percentage is equal to 2 twice, thrice, and so on. And what are the x and y percentages here? And x y percentages or amount of substance consumed or amount of reactant consumed. If you take one example, and here we will derive one relation here based on that formula. The relation between T 99.9 percentage and T 50 percentage. I should write that T x percentage 99.9 percentage by T 50 percentage is equals to log of 100 by, this is 100 minus 99.9, again log 100 by, this is 100 minus 50. Here 99.9 means we will get 0.1, 0.1 means this is log of 10 power 3. And this one will get log 2, log 100 by 50 log 2. And log 10 3 means 3 by, this is log 2 means 0.3. 3 by 0.3 means it is 10. So log t 99.9 percentage by t 50 percentage is equals to 10. So t 99.9 percentage is equals to 10 times of t 50 percentage. So like this you can derive the relation between two time intervals, the two percentages x and y. Okay, now we will see some graphical representations for the first order reaction. Graphs also very important for first order. Graphs. First graph, rate versus concentration. Rate of reaction and the concentration, initial concentration of the reactant. What formula we have? Rate is equals to rate constant into A, like y equal to mx. You will get the graph like this. And next, rate versus time. What is the formula? Rate is equals to K into, what is the concentration of A at a time t? With respect to time we are taking, so means K into at a time t. We have AT is equals to e power A0 into e power minus KT. Initial concentration into e power minus KT. Again, like y equal to, this is a exponential graph, and as the time increases, anyhow the concentration of reactant decreases. If the concentration of reactant decreases, rate also decreases, but it is exponential decay. You can see the graph like this with respect to rate versus time. And the next graph, we will take the next graph with respect to ln of AT, logarithms. Ln of AT, or we can take in place of AT, sometimes they will give like this, ln of A0 minus x or A minus x. Anyone you can take. What formula we have? Ln of AT is equals to ln of A0 minus KT. This is the formula. It is look like y equal to minus mx plus c, negative slope, and this is versus time. The graph is between ln of AT versus time. So it is a intercept of ln of A0 and the slope. What is the slope of the graph? Minus k. The same graph we can take with respect to the log. There is a natural logarithm ln, and if you take in terms of the log with the base 10, and this is with the base e. If I take log of AT or log of A0 minus x versus time, again the formula same, but here we have log of AT is equals to log of A0 minus, if you convert ln into log, you will get 2.303. So KT by 2.303. This is the formula. Again, look like the y equal to minus mx plus c, same graph, and our intercept here log A0, or you can say log A, initial small a, but slope is different here. Previous case slope is minus k, but here slope is minus k by 2.303. And this is important. Here k by 2.303 is the slope. You should very careful about this log and ln graphs. And here both the graphs looks the same, intercept is different and that slope is different, the values, points are the same. And the next graph, a concentration of reactant versus time. So, with respect to time, how the concentration of reactant is decayed. Again we have the formula AT is equals to A0 e power minus KT. Again with respect to time, the concentration of A is decreased. Again this is exponential decay. So, we will get the graph like this. This is exponential decay. And when it will become 0? Here if you take AT equal to 0, at time t the concentration of reactant is 0, means completely the reactant is consumed, then that is equals to A0 e power minus KT. Anyhow here initial concentration is not equal to 0 and this should be e power minus KT should be equal to 0. And when this is possible, e power minus KT equal to 0 means here time t should be approaches to infinity. Just now we have discussed initially that to complete the reaction we required infinity times of half-lives. So, similarly to consume 100% of the reactant, so we required infinity time. So, that is why you will get exponential decay, but it will not touch the x-axis, it will go like this, almost approaches to the 0. So, concentration of the reactant will keep on decreasing exponentially. And similarly concentration of product versus time graph. Concentration of product versus time. What formula we have? Concentration of product means we left with x. X is the concentration of the product. Formula A0 into 1 minus e power minus KT. Again exponential form. Means as time increases, concentration of product will increase, but this is exponential. Again you will get the graph like this. And here the maximum amount, it should not be exceed A0. I get somewhere we have the point. Let us assume this is A0. It will almost closest to the A0, but not equal to A0. Just like this opposite graph. Concentration of product versus time. And the next one more last graph. This is very very important again. Half-life versus initial concentration. T off versus initial concentration. Initial concentration you can take A0 here. So, we know that half-life of first order reaction is independent on the initial concentration. Whatever the initial concentration, half-life is always constant. But in case of zero order reaction, you will get a line which passes to the origin. Here we will get a constant line. We will see some examples related to the first order reaction. Again these are purely experimental based, you have to remember, memory based again. Mostly all radioactive disintegration reactions comes under first order reactions. Simply we can say nuclear reactions. Nuclear reactions or first order reactions. And hydrolysis of ester and hydrolysis of sugar, this comes under first order. Ester hydrolysis. You can take example if you want. Hydrolysis of ester, I think we have taken already. Let us take ethyl acetate and do the hydrolysis. We will get acetic acid plus ethyl alcohol and sugar. and sugar also can undergo hydrolysis, mostly in presence of acidic medium. It can form glucose and fructose, and both are having same chemical formula but structurally different, and one is the glucose, another one fructose. And decompose some of the decomposition reactions: decomposition of nitrogen pentoxide, 2NO2 plus of O2, and decomposition of hydrogen peroxide, H2O2, and it also comes under first order reactions of O2, and decomposition of SO2Cl2, decomposition of ammonium nitrite, these are the few examples comes under first order reactions. Next is some characteristics of first order reaction as like zero order. Again here equal fraction or equal percentage of reactant reacts in equal time period. We can take the statement: equal fraction or percentage of reactant reacts in equal time period. Means what? Again, let us take initially we have 100% of the reactant. To convert this 100% to 90%, means how much amount is decomposed here? The percentage of reactant reacted is 10%. Again 92, we have to take equal fractions or equal percentage of reactant should be decreased. So 100 to 90, 10%. Again 90, 10% of 90 means 9. Again if you 10% of reactant reacts, it will give 81. Again 10% in the 81, 8.1, that can give 72.9, and so on. And this is a equal fractions or percentage of reactant is reacting like this. So this can react with equal time period. Let us assume to consume 100 to 90, we require again 5 minutes. Again 90 to 81, the time required is 5 minutes only. Again 81 to 72.5, again the time required is 5 minutes only, and so on. And that is the characteristic property of the first order reaction. Equal percentage of reactant will react with equal time period. Next one more. A concentration of reactant remaining after equal time periods. This is 90, 81, 72, whatever it is. And they can form a geometric progression. You can take concentration of reactant remaining after equal time period. Constitute a geometric progression. Your GP. In case of zero order reaction, we have AP, but here it is ZP. Means what again? We have the formula. After some time, the concentration of reactant AT is equals to A0 into e power minus KT. This is the formula we have. Let us assume T equal to 0. In place of T, now you take at 0 time, we have 0 and at time t we have a0 e power minus kt, and at 2t we have a0 e power minus 2 kt, and at time 3t you can take here we will get a0 e power minus 3 kt, and so on. Now you see the difference here, common difference means common ratio. The previous case we have the difference, here common ratio a0 to a0 e power minus 2. What is the common ratio here? Common ratio is equals to e power minus kt. Again between these two the common ratio is e power minus kt. Again here the common ratio is e power minus kt. So like this they can form geometric progression in case of first order reactions. So next the numericals about this first order reaction we will see in the next class.